These are the notes on types of nuclear decay and nuclear reactions. It'll be helpful to have a periodic table accessible. In the crash course video that you watched, you should have been introduced to alpha decay or alpha rays as a type of nuclear decay, beta particles or beta rays, and gamma rays. We are going to talk about how we can write those types of decay into a nuclear reaction today. In that video, it also discussed kind of the relative strength of those. An alpha particle can be stopped by paper, a beta particle or a beta ray can be stopped by aluminum, gamma rays need lead to be stopped, and things like neutrons could be stopped by concrete, but none of the other things. All right, so alpha decay, or you might hear this as alpha particle emission. This occurs in elements that have really high masses, and so we see masses of that 200 plus. When we were looking at the kind of stability graph on those previous notes of what does it mean if an atom is radioactive, we saw that as that mass increased, that proton to neutron ratio was farther off. And so by decaying into two smaller particles or emitting a helium atom, then that can make that nucleus smaller in size, and that is one way to become more stable. The penetrating power of an alpha particle or a helium atom is low. It can be shielded by paper or clothing. We can model, we talked about this notation of how can we write out uranium-238 showing that atomic mass and the protons here, because that's where those changes are happening. And so we can see a parent nuclide, which is unstable, can decay into a daughter nuclide that is more stable, and by emitting an alpha particle, which is a helium atom. And so we write nuclear reactions just like we write our other reactions we have throughout the year, our chemical reactions. But as we're looking at it, this balancing needs to come from the numbers. We need to have the same mass at the start as at the end, and we need to have the same protons at the start as at the end as well. So because of this helium particle that is decayed, or that is breaking off from that, in this case, sorry, this is a different example, because that helium particle breaking off and that helium particle breaking off here as well, that is called alpha decay or alpha particle emission. Next is beta decay or beta particle emission, and this happens when you have a skewed proton to neutron ratio, and generally with a little bit smaller atoms than our alpha decay. And so with that skewed proton to neutron ratio, again, it's when that ratio is not balanced that an atom can be unstable. And so in order to get that to become more stable, a particle, such as an electron, is emitted, and that beta particle has no mass, but that charge is taken into account with that -1 for our in our protons. And so that electron ends up being decayed. And what's actually happening here is that by losing a neutron, that is going to break up into a proton, and then that electron's charge is going to break off. So we see that as an electron. The penetrating power of beta decay is moderate, so stronger than alpha decay, but not our strongest type of radiation. So things like tinfoil could block that. And again, we see this modeled in a nuclear reaction where that parent nuclide, iodine-131, decays into xenon-131 and a beta particle, which is an electron. Next, we have gamma radiation. And gamma radiation occurs when an atom has too much energy. And so a gamma ray, and this is not a particle, it is a ray of energy, or a photon, is emitted. And the power of this radiation is high. You need lead or concrete to block it. And we denote this because we're not actually going to be changing our element. Our gamma particle or our gamma ray has a 0 and a 0 here because it has no mass. So we denote that our parent nuclide, in this case barium-137, has high energy with an asterisk. And then we can see that energy being released, and then we get a more stable low energy barium-137 particle. All right, and then the last type of particle that can be emitted, this was not discussed in that kind of intro video, is positron emission. Positron emission occurs when a nucleus has too many protons, so the atom converts a proton to a neutron, releasing the positive charge as a positron. And this is really similar to what we see pictured here with that beta decay, because it is the same process. It is also known as beta plus decay instead of beta minus, where beta minus is an electron with a negative charge. A positron is a particle with the same mass as an electron, but that positive charge, and so that's how that charge gets emitted from that proton then becoming a neutron. And so our particle in this case is similar to that electron, but with a positive one instead of a negative one. And we can see that modeled here. So we've seen some examples of nuclear reactions, and if we look that reaction below showing uranium-235 decaying, notice the sum of our masses. When we're figuring out maybe a missing piece of this puzzle, we look at using those masses to determine the missing mass. We can look at the bottom numbers, which are those protons, and we can then figure out, okay, what is a missing piece based on that proton? And again, those symbols correspond to the protons in the element that they are with. I put a periodic table in here for us because we do need those protons. We are going to rely on the symbols to tell us what isotope we're dealing with. We're not using our masses from our periodic table because, again, that's the average atomic mass. So let's go ahead and fill in the missing atom to make the nuclear reaction complete, and then we can identify the type of decay that occurs. So as I look at this first one, I don't know what is decaying, but I can see that because this is an electron, this is beta decay. And so then I can look at, because again, it also says identify the type of decay. So I can see that this is a beta particle because that is an electron. If I'm figuring out, well, what was this before it decayed, I can look at, well, 0 plus 14 needs to equal whatever I started with. So 0 plus 14 is 14. Same thing with my bottom numbers now. -1 plus 7 needs to equal whatever I started with. -1 plus 7 is 6. Well, how can I figure out what element that is? I can go up to my periodic table, and carbon is number 6. And so then I can fill in the symbol once I know the protons. So carbon-14 undergoes beta decay to emit an electron, and nitrogen-14. All right, looking at this next one. This one is because of this helium particle here. This is alpha decay. Sometimes, in order to undergo this decay, you might have a particle colliding with something else and then emitting an alpha particle or a beta particle and undergoing that decay. So in this case, we do have something that maybe collides with helium to produce that carbon-12 and helium-4. So how can we go ahead and look at this? Well, our numbers on the top, something plus 1 needs to equal 12 plus 4. Well, on the right, that 12 plus 4 is 16. So 1 plus something needs to equal 16. So that is going to have a mass of 15 in order for our reactants and product total masses to be balanced. Same thing with our numbers on the bottom. I've got 6 plus 2 on the right. Well, that's 8. 1 plus what gives me 8? That's going to need to be a 7. And I can look at my periodic table, and nitrogen is element 7. So I can fill in the symbol once I know those protons. Next one, we have radon-222, and that is decaying into radon-222. Well, we're not losing anything with mass because our element is not changing, our atom is not changing, but this star means that we have high energy radon. And so then we have this without a star, that's going to have lower energy. Well, how does it get to that part? It is going to go through gamma decay, and it's going to release a gamma ray. That symbol, that Greek letter gamma, is our symbol, and then that has no mass and no protons. So we can fill that in. All right, if you want, go ahead and try the next three. If you get the hang of it, you're welcome to move on. I'm going to just go ahead and show you the answers. Take a look at those, write them down if you need, and then we're going to continue. All right, so when we're writing a nuclear reaction, a couple of things that we can look at. So we might have radiation as a reactant. So if something is being captured, absorbed, takes in, gains, then we might need to write something on that reactant side. If we look at this example in number 2, nitrogen 15 captures helium-1 to undergo alpha decay is how we could say that, because then we would know that a helium particle is going to be emitted and we could figure out what else gets emitted through that. So this is an example where you could use any of these 4 terms. Radiation as a product now, decays, emits, gives off, loses. We could say here radon 222 undergoes gamma decay, or emits a gamma ray, undergoes that gamma decay, any of those sort of things where you're saying what that particle is, loses something. So we aren't usually told everything that in if we're talking about a nuclear reaction, because we can figure out those missing pieces using our periodic table like we did to fill in the blanks here. All right, so our last piece here, writing a balanced nuclear reaction for each of the following. So we are going to have some things that we're going to need to fill in. If you feel comfortable, you're welcome to go ahead and try these on your own, and then check back with the answers. So U-238 emits an alpha particle. Well, this is telling me that I'm using uranium-238, the isotope is specified, and I need to go to my periodic table to figure out, well, where is uranium? So when I look, uranium is number 92, and so those are going to be the protons. So emits an alpha particle, so that means it's undergoing a process where now an alpha particle, well, what is an alpha particle? That is a helium atom, and I know that an alpha particle is always going to be that helium-4 plus. So something is going to be left over. We need to fill that in, just like in the slide previously, where we were just filling in the blank. So then we can go through and look. 238 needs to equal 4 plus something. So I'm going to just go 238 minus 4. That's going to give me 234. That's how much mass I'm going to need. Same thing on the bottom here. 92 needs to equal 2 plus something. Well, 92 minus 2, that's going to be 90. And then I'm going to my periodic table, and I can find that element 90 is TH, which I believe is thorium. All right, next one. Carbon 14 undergoes beta decay. Well, we've got carbon 14. I need to go to my periodic table, and I can figure out that carbon has 6 protons. Undergoes beta decay. Well, beta decay is when an electron is emitted, and so that beta particle is that 0, -1 with the E. And then we can figure out, well, what are we missing? As we're looking at this, 14 needs to equal 0 plus something. Beta decay is nice because that top number is not changing. It does get a little tricky though when we start to look at 6 needs to equal -1 plus something, because that electron is a -1. And so we have -1 plus what equals 6. That is going to be 7. So it is going up on that periodic table when we kind of mental math. Often people would put 5. And I can check, and that is nitrogen on my periodic table. Pa234 emits gamma radiation. And so we're looking at Pa 234, I can go to my periodic table, and that's number 91. Emits gamma radiation. Well, a gamma ray is that gamma symbol with no mass and no protons. And so if I look at that, I'm going to need to have 234 and 91, which is Pa again. So how do we distinguish this? Well, we need to put that star. So we put gamma radiation. We need that star along with the gamma particle. That shows that this is high energy, and then it is losing that energy to become more stable. Ag106 captures an electron. Now we're seeing that word capture. That means that to become more stable, our Ag106, which as I look at my periodic table has a mass of 47, if it's capturing an electron, then that's going to be plus that electron. And then forming something that's more stable. As I look, my 106 plus 0 needs to equal that 106. Same thing with our bottom numbers. 47 minus 1 is going to be 46. And then we get that that is PD. And now this might go and this might undergo now a different type of decay in order to become more stable, but this might be the first step of the process. All right, last one, K38, so potassium 38. My periodic table tells me potassium is number 19. Emits a positron. That positron, that's that last type of decay that we had talked about, where an electron, it's an electron with a positive charge, so we still use that E. We wouldn't use a capital P because that would represent a proton, which we wouldn't necessarily use. Or capital P is phosphorus. But because, again, this has the mass of an electron, but with a positive charge, that's why we use that positive E. And this is the same as beta plus decay. So then we have that positron, and when it emits it, what do we have left? Well, looking at, again, doing our math, 38 needs to equal 0 plus something, so there's a 38. And then we do have that positive one now on the right, so 19 needs to equal 1 plus what? And so that is going to be an 18 here, which is argon, which is a noble gas, and we know noble gases are very stable. All right, there is a worksheet and a check-in for you to use as practice. Reach out to your teacher with any questions.